Hello everyone. We are in chapter 12. Today we're going to be talking about sections 12.1, 12.2, and 12.3, introducing the concept of linear regression and correlation. In these sections, we're going to be looking at a topic that is somewhat different than what we've been working with the last few chapters. But then when we reconvene in 12.4, we'll see how this topic does relate back to the idea of hypothesis testing. So to start off, we need to introduce the concept of a linear equation, something that we encounter in algebra. So a linear equation in two variables is an equation where the highest exponent on the given variables is 1. So the typical standard form of a linear equation is ax plus by equals c. This is our standard form. You've got x's, you've got y's. You will also usually see it written in what we call slope-intercept form, which is that y equals mx plus b form. This is probably the most recognizable version of this formula that you would see in algebra. Now, when we're talking about a line, an algebraic line, the graph of a line, it needs a couple of things. The first and most important one is the slope of the line. This measures the line's steepness. So the value for the slope is giving us, kind of colloquially, we say rise over run. So it's how much we're going up divided by how much we're moving over. And in that process of moving from one point to another, we create a line. The slope of that line tells us how steep of an increase we've gone. So if we're going significantly more rise than run, that's a steep line. Whereas if we're going a little bit of rise and a lot of run, that's a very shallow line. So the slope gives us a good indicator of how the line is moving, how the line is changing. Now, in order to find the value for the slope using m, we find this using either delta y over delta x, change in y over change in x, however you want to think about it. Oftentimes, if you're working with the line between 2 points, you would say y2 minus y1 over x2 minus x1. We can take this concept of slope and interpret that within many different contexts, and we'll see an example of that in just a little bit. But when it comes to graphing the line, we use the slope to tell where the line is going. So here we have slope-intercept form of a line. So this is the one that I was just talking about. We have y equals mx plus b. This equation of a line gives us the slope given by m and the y-intercept given by the point 0, comma b, where b is this value. So if we want to graph the line in slope-intercept form, so for this example, y equals negative 2x plus 1. So m is negative 2, so that's our slope. And b is 1, so our y-intercept is the point 0, 1. We can graph this. We can plot this point at 0, 1. And now our slope of negative 2, this is the same thing as negative 2 over 1. So negative 2 means we go down 2, right 1. Okay, we always go to the right, so we never turn around and go to the left. It's always to the right. The question is just whether we go up or down, and the negative tells us that we are going down. So we go down 2 over 1, down 2 over 1, down 2 over 1. If you want to backtrack a couple of points, we get these. And then we can connect the dots as smoothly as possible. Hopefully better than what I'm doing right now. You get the idea. So that would be the graph of the line. Okay, so we can graph lines using the slope, using the y-intercept, that vertical intercept. But we also want to be able to make interpretations about situations, about modeling problems, about real-world application using slopes and intercepts like this. So if we look at the next page, we're looking at the slope again. We have the value m, but this time we're looking at it in a more contextual sense because the slope gives us what we call the average rate of change for a linear function. Rate of change is just how much the function is changing over time. So the slope gives us that rate of change in terms of output units per input units. So like miles per hour is a great example of that. We can interpret slopes in contexts, we can interpret variables in context, and we can interpret intercepts in context. So if we look at this example here, the cost, C of x, where x is the number of miles driven of renting a car for a day, is $48 plus $1.55 per mile. What is the independent variable and its units? So the independent variable here, that's going to be the input variable, the x here. It is independent because that represents the number of miles driven. We're the ones, if we're driving the car, we're the ones deciding how many miles to drive in the car. So the units on this, of course, are miles. Now, what is the dependent variable and its units? Well, the dependent variable is once you put in the number of miles that we've driven, what do we get out? We get out C of x, which is the cost of driving that many miles. So the dependent variable is C of x. It is dependent because it purely depends on how many miles we drove. If you drive more miles, you're going to pay more money. The units on this would be dollars. Now, for the slope of this linear function, this is the rate of change. So if we look at what the situation is telling us, we rented a car for a day. It costs $48 plus $1.55 per mile. So the rate of change is going to be that 1.55. And the units on that are in dollars per mile. So for every extra mile driven, it's costing us $1.55 more. Okay, so that is our rate of change for this function, for this line. What is the y-intercept? So this vertical intercept, we have the initial cost here is $48 plus that $1.55 per mile. The 48 is like our starting point. That's when we haven't driven any miles yet. That is going to be the y-intercept. So the y-intercept is 48. Units are dollars. And the function that we create here is the function C of x equals 1.55x plus 48. So if at any time we wanted to determine how much this rental car was going to cost us, we could plug in the number of miles that we're going to drive for x, and then we would get out the total cost that we would be spending on the rental car. Okay, and we would be paying $48 no matter what. That's the initial value, that y-intercept, plus $1.55 per mile driven after that. So now that we have kind of the basics down for what is a line, how do we graph a line, how do we interpret the components of a line, now we need to look at the concept of a scatter plot. So a scatter plot, also called a scatter diagram, is going to be a tool that we can use in relating variables to each other. And we'll see in the upcoming sections how the line that we talked about in section 1 relates to the scatter plot in section 2. So when it comes to drawing and interpreting scatter diagrams or scatter plots, so this is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is on the horizontal axis and the response variable plotted on the vertical axis. So we're going to have two variables that are both being recorded for one individual. The two values of those variables are put together and are used to plot a point. So like a point x comma y kind of thing. Once we plot enough of those points, we will have a collection of points on the graph. That is the scatter diagram. That is the scatter plot. And then we can start to draw conclusions about what that scatter plot tells us after we have drawn it. So let's take a look at this example. So the data shown below are based on a study for drilling rock. So we're comparing the depth at which drilling begins in feet and the time to drill in minutes. So we're seeing, okay, if I start drilling 35 feet down, it's going to take 5.88 minutes to drill a certain distance, to drill 5 feet into the rock. Whereas if we start at 130 feet down, it's going to take 6.93 seconds to drill 5 feet into the rock. So we're going to take these points and plot them. So we're looking at drilling depth is the explanatory variable, so that's x, and the time in minutes to drill 5 feet is the response variable, so that's y. So we're looking at x and y. So here is our scatter plot that we're going to draw. So if you have the chart in front of you, you can go ahead and start plotting points here, but we're going to have 35 feet results in 5.88 minutes. So that's going to be right around here. 50 feet is 5.99 minutes. So that's right there. We're going to have 75 feet and 6.74 minutes. So right about there. 95 feet and 6.1. And then we go up to 120 and 7.47. 130 gives us 6.93. So right about there. 145 gives us 6.42. So right about there. 155 gives us 7.97, so way up here. 160 gives us 7.92, so just a little bit below that one. 175 gives us 7.62, so that's going to be closer to here. 185 gives us 6.89. That's going to be right about there. And 190 gives us 7.9, which is going to be right around there. And this is our scatter diagram, our scatter plot. Now, the question that we want to ask is there any relationship between these variables? So do we see like a definitive pattern in this diagram? So you see, like, if we kind of follow the flow of these They do seem like they're kind of trending upward a little bit, like they're kind of heading in this direction. But it's not a perfect relationship, right? They're not all like just perfectly in a line like this. But it seems like they might have some sort of relationship. There might be something there to say that the depth and the time that it takes to drill are related. Now, there are a few different ways that these variables could be related. We could have a relationship that is linear, which is when the points on the scatter diagram follow the general pattern of a line. A relationship can be nonlinear when the points follow a general pattern, but it is not a line. And we say that there is no correlation when the points do not show any pattern at all. So if we look at these graphs on the top of the next page here, so we have a linear association, we have a nonlinear association, but it definitely still has a pattern to it, as opposed to one like this, where if I draw like a line through that, that's not really giving a good representation of the points, right? Like these ones are kind of here, but then these ones are here, and then these ones are here. Like there's not a definitive pattern to these. They're just kind of jumbled all over the place. So that one we would say potentially no correlation. We are going to be focused on the linear cases. As you can see from the title of the chapter, we're looking at the concept of linear regression. So it makes sense that we would want to talk about the linear relationships. So if there is a linear relationship between two variables, it can go one of two ways. It can be positively associated, and that would be kind of like this first one. So a positively associated relationship is when above average values of one variable are associated with above average values of the other, and then vice versa. So whenever one value of the variable increases, the value of the other increases with it. Okay? Or in other words, it has a positive slope, right? So this variable goes up, and so does this one. So we go up, and then we go up, and then we go up, and it's following that pattern. The variables can be negatively associated when above average values of one are associated with below average values of the other. So whenever the value of one variable increases, the value of the other decreases. Or in other words, they have a negative slope for that line. So we're focused primarily on the linear relationships, the linear correlations between variables, and we're looking at either positive or negatively associated variables. So let's bring it all together. Let's talk about how our work with lines combines with our work with scatter plots or scatter diagrams. So this is what we call the least squares regression line, or the line of best fit. This is the line that minimizes the sum of the squared errors. In other words, it is the line that best fits the data set in our scatter plot. Okay, so we're looking for a line that is as close of a fit as we can possibly get to the data set as it's given. So we are representing this line using a linear equation, right? The typical y equals mx plus b format. They have like ways of determining slope and y-intercept here. We're going to be using the technology for that, so we're not going to need to worry about doing these calculations by hand, like it says right here. So we're going to be using the technology to give us the scatter diagrams and to give us the lines. We just have to input the right stuff. So using the data from example 12.4, so the drilling data, find the least squares regression line and draw the least squares regression line on the scatter diagram of the data. So we're going to use Desmos for this. So if we take a look, I went ahead and already inputted the data here, but just so that you know how to do it, if you want to input a table like this with two variables in it, you just go to this plus sign up at the top corner above the fields that you type into, add item, and then right there on the list is table. And it will pop up this table, and then you can just go in and just keep adding like as many different values as you need. But I went ahead and did that already for this one. And then if we check this magnifying glass, there it is. So this is our data set for the drilling data. And if we look back and compare it to how we did before, it should look about the same. The scale might be a little different than what we had done just because they wanted to fit in this space. But this is the drilling data. So we're taking Desmos and we're making a table. Now, when it comes to actually creating the least squares regression line, there's one thing that we have to do in order to make this work. So the variables in this table are x1 and y1. We can call them whatever we want, but I'm just going to stick with x1 and y1. So we're going to take y sub 1. So y1. Now, normally, we would use the equation y equals mx plus b. But in order for Desmos to understand that we're taking this from the table, we're not going to use equals. We actually have to use this tilde symbol, so this kind of squiggly one down here on the bottom. So we're going to do y1 squiggle, and then we'll do mx plus b, but not x, because it's x1 is the variable in the table. So mx1 plus b. And if you look at what that has given us, we now have the least squares regression line, so our line of best fit. It did us the favor of graphing for us, so we have the line on the graph, and we have the parameters down here, so we know what m is, and we know what b is. So we can actually just use those to create the linear equation. So we're going to use, so y1 tilde mx1 plus b. So we get y equals, so we're looking at 0.011553 x plus 5.52727. So 0.011553x plus 5.52727. So that is the equation of the line of best fit, our least squares regression line. This is the line that best fits that data set. So if we were to shift the line up or down, if we were to change the slope and tilt the line, it would not fit the data as well as it does right now. And you can see, like, kind of as we're going through it here, it does seem to be kind of going right down the middle of where that data is. You've got some pulling it a little bit farther, kind of down here. You've got some that are hanging kind of close to it, like these ones. But that seems to be a pretty good fit. And in fact, it is the best fit. Right. This word of caution that they give, so remember, it's always important to plot the scatter diagram first. If the scatter plot indicates that there's a linear relationship, then it's reasonable to use a best fit line. But not necessarily for values outside of that domain. And we'll talk more about kind of keeping it within the scope of the model here. But we want to check the scatter diagram first before we just start graphing lines for no reason. So now to the topic of residuals. The residual of a value is the difference between the observed value and the predicted value of y, of that output. Okay, this is the residual, also referred to as error. So because the line is not going to hit every single point, because the points are not in a line. So there will be some error from point to point, right? The line is not going to hit all of them. And like in the case of the one we were looking at, I don't think it hit any of them exactly. It came close. But the residuals will tell us how far off we were from the predicted value and the observed value. So, for example, predict the drilling time if drilling starts at 130 feet. So, we go to the line, and we find the value of 130, and we get 7.029. 7.029. So we have the point 130, comma, 7.029 on the line. So if drilling starts at 130 feet, we predict a drilling time of 7.029 minutes. So then if we compare that to the observed drilling time at 130 feet, that was this one? Yes, this point right here. So 130, 6.93. So it's asking, is that like above or below average? It is below average because if you look, it is right below the line. It's not that far below, but it is below slightly. So it is slightly below. And that's, of course, 6.93 minutes. So we have the observed time versus the predicted time. So the line was not that bad of a guess. The line gave us a value not that far off. So the residual, this is giving us information about how far off we were. Now, the nice thing about what Desmos can do for us is if you look in this box where we graphed, where we got the line from, right down here, there's a button that says residuals, E1, so like error 1, and it says plot. If we go ahead and click that button, and look what it did for us. It gave us a third column in the table. That third column is all of the errors or the residuals from each of these values compared to the regression line. So, and actually I think Desmos does graph these too. Yeah, here they are down here. So this is telling us how far off of the line we are for these points. If I can get it to show both, yeah. So it's kind of just taking that relationship as it relates to the line and showing how close or far the line is from all of these points. So for the point in question, our residual is right here, negative 0.099157112. So negative 0.099157112. So not too far off. All right, we're only looking at a residual of negative 0.1 almost. Now, when it comes to interpreting results from the line, we can see how the line relates to the scatter plot, but let's talk about how the line explains what's going on in the scenario. So interpret the slope and the y-intercept for the line obtained in 12.4. So the slope, we're looking at a rate of change of the number of minutes it takes to drill 5 feet as our depth changes. So the slope we got was 0.011553, so back on the last page. So the drilling time increases by 0.011553 minutes per foot. So for every foot deeper that we start drilling, we are adding on average this much time to our drilling time. So I'll actually put that on average because it's not exact. The line is just an approximation. So on average, our drilling time increases by 0.01 minutes, roughly, for every foot that we go down. So the y-intercept, so the vertical intercept here, this represents like our initial value or our starting point. So this is the initial drilling depth is 5.52727. Or excuse me, that's, sorry, let me fix this. So as the initial value, sorry, the drilling depth is the input. So when drilling at 0 feet deep, drilling time is 5.52727 minutes. That's better. So our initial drilling time when starting at 0 feet of depth is about 5.5 minutes. So that is our starting point, so to speak. Now, when it comes to making interpretations and conclusions about the data based on the line, we have to be very careful that we stay within what we call the scope of the model. Because if a researcher is working outside the scope of the model is no longer applicable. It's not going to be effective or helpful. So we should never use the least squares regression line to make predictions outside the scope of the model because we can't be sure that the linear regression continues to exist. So if we have, all these data points that look like they're forming a line like this, if we use this line and continue going this way, what if the data all turns as we go? And we wouldn't know that using the line. And then all of a sudden we're predicting values way up here when actually they should be way down here. And we wouldn't know that because we are, again, beyond the scope of the model. So we should never use the regression line to make predictions outside of the data set. We don't want to go beyond the data. Okay, we want to stay within the scope of our model because otherwise, who knows what the data is going to do? It's not even necessarily going to be linear anymore. Now, the next thing to talk about is the idea of the linear correlation coefficient. The linear correlation coefficient talks about the strength of the linear relation between the two quantitative variables. So we're going to be able to find, and I know there's a big calculation there on the page, we're going to use technology for it, but we're going to be able to determine how strong of a relationship two variables have with each other based on only the scatter diagram and the least squares regression line. Okay, so ignore that calculation there. We'll see how we use it in just a minute. But first, a couple notes about this linear correlation coefficient R. So R is a unitless measure. It is always between -1 and 1. Positive values of R correspond to positive relations. Negative values of R correspond to negative relations. The closer it is to 1, the stronger the positive relation. If R is 1, there is a perfect positive relation. So in other words, that means that the data is a line. Like there's no variation from it whatsoever. If the value is closer to -1, this is a stronger negative relation. When R is -1, there's a perfect negative relation. So again, it's still a linear relationship, but it's going down instead of up. That's the only difference. And the closer that R is to 0, the less of a linear relation, either positive or negative. So we have to be very careful with how we describe this because some people get a little confused and they say like a negative 0.99 value of R means, oh, it's more negative, which means that, they're not related. Actually, this means they are very related, but in the negative direction, so going down. Or if it was, positive 0.99, that's a very strong positive relationship. But if the value is, 0.00001, something really close to 0, then we're talking about not much of a correlation at all. These are points that, are just kind of all over the place, and they don't really seem to have any relationship between them. So this is what the correlation coefficient tells us. Now, how do we find R? How do we find the correlation coefficient? So looking at our same example in Desmos, the nice thing is Desmos already knows that we want this value, and so it gives it to us right here. So we have R is 0.7728 for our example. So we have R is 0.7728. This value is fairly close to 1. It's certainly closer to 1 than it is to 0. So there does appear to be a relatively strong correlation between the variables, and it is a positive correlation because the value itself is positive. So we have a strong positive linear correlation between drilling depth and drilling time. So there does appear to be a relationship between the two variables, and it appears to be a positively associated linear relationship. So as one goes up, the other goes up too, right? So as our drilling depth increases, as we go further down, the amount of time it takes to drill increases as well, right? And you think about like the rock gets harder, right? And more solid as you make it deeper into the Earth's core. So you're looking at increased drilling times to go along with it. We can also find what we call the coefficient of determination given by R squared. Now, notationally, we use capital R squared. Desmos is going to use little r squared. It basically is giving the same thing because the calculation is the same. It's just R squared. But this measures the percent of total variation in the response variable that is explained by the least squares regression line. So it measures how well the line describes the relationship between the variables. So how well the line describes the relationship. Okay, so if we get a very low value for r squared, that means that this probably isn't a good idea to use the line. Okay, even if it gives us a stronger correlation, if the coefficient of determination is low, that's telling us, okay, maybe the line isn't the best choice. Maybe there is a relationship still, but maybe it's something else. Maybe it's like parabolic. Maybe it's, cubic, whatever the case may be. But maybe the line isn't the best way to go. So all the values of r squared are going to be between 0 and 1, because you're squaring it, so it's going to be always positive. If r squared is close to 0, this indicates a model with very little explanatory power. R squared close to 1 indicates a model with much explanatory power. Okay, so the closer we are to 1, the better the line is for describing the relationship between the variables. So determine the coefficient of determination r squared for that same example and interpret that value in context. So r squared is also given to us. I mentioned Desmos uses little r, but that's this value right here. So we have r squared is 0.5973. So this means the line has 59.73% explanatory power. So fairly strong. So that means that the line probably is a pretty good way to go. In this case, there's not really a better type of curve or shape to describe that relationship, at least not on the surface. There might be an actual better one, but just looking at this, we have about 60% explanatory power, which is a pretty good relationship. That's a pretty strong indicator that this line is a good use for this relationship of variables. To determine r squared, simply square the value of the linear correlation coefficient. So again, it is just r squared. This process of squaring r only works for the least squares regression model. It doesn't work in general. Now, the nice thing for our purposes in here is we're only working with least squares regression models. We're not working in general with other types of models. If we were, we would have to come up with other ways to find it. But luckily for us, we don't need to do that. Now, an important thing to take note of here, we've been talking about the relationships between variables and whether or not they correlate with each other. They have a linear correlation. It's very, very important to mention correlation is not causation. So just because two variables are correlated does not mean that one causes the other to change. And this is where we get into all kinds of problems with people interpreting results of data. People saying, I found this result and I found this other result, and they both happened at the same time. So that means that this one must cause the second one. And that's just a fallacy. That's irrational thought. Just because two things both occur at the same time or even at a same rate, or they correlate very strongly, does not mean that one automatically causes the other to happen. This works with like medical studies, with scientific studies. They can't give you 100% certainty that a drug causes a number of symptoms or causes a reduction in symptoms. All they can say is there is a strong correlation between people who use our drug and people who have, reduced symptoms. So, like, for example, according to data obtained from the Statistical Abstract of the US, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers? So this is a very strong correlation coefficient. So 0.940, that's very, very close to 1. But the question, does that mean that the higher percentage of females with bachelor's degrees causes the birth rate to increase for unmarried mothers? Not necessarily. And again, we're in a position where we can't say anything with certainty. And, who knows? That might be a factor in causing this birth rate to increase for unmarried mothers. It might not be a factor. We cannot make that conclusion just based off of this information, off of a correlation between the two. So just because the two correlate does not mean one caused the other. Okay. So, very important takeaway. Correlation is not the same thing as causation. Now, when can we claim causation in a relationship? Well, not too often. It depends on how the experiment was set up. When data are observational, we cannot claim a causal relation. So if you're just observing things that are occurring and writing down the data, you cannot claim that one causes the other. We can only claim causality when the data are collected through a designed experiment. So when we have eliminated the other variables, we have eliminated all other possibilities. There are no potential lurking variables or confounding that could be occurring in an experiment because we've taken care of them. So if that's the case, then yeah, we can talk about okay, maybe one of these things does cause the other to occur because we've eliminated all the other possible things that could have caused that change. So, but when we're working with observational studies, you can have the presence of, again, what we call a lurking variable. This is a variable that is related to both the explanatory and response variables, and it could be what explains the change. It could be that this lurking variable is causing a relationship between the other two, even though they don't cause each other. It also could be that there just is no relation, that it's just a coincidence. That certainly can happen as well, as evidenced by an example like this one. Ice cream sales and crime rates have a very high correlation. So basically, the more ice cream that is sold, the higher the crime rate is. Does this mean that local governments should shut down all ice cream shops? Because according to this correlation, the more ice cream they sell, the higher the crime rates. So if we lower the ice cream sales, that should lower the crime rates. These are the kinds of arguments that people make when they don't necessarily understand or want us to understand what their data is talking about. So should they shut down all the ice cream shops? No. Ice cream sales do not cause higher crime. Now, this, of course, is somewhat of ridiculous of an example, but when you're looking at two things that maybe seem like they could be related to each other, that's when people start manipulating the results to make conclusions. Because obviously this example, ice cream sales are not causing higher crime rates, But, what if it was something else that maybe was a little more tangentially related to crime rates, and then someone wanted to make conclusions based off of that? It might sound more plausible, but it doesn't make it true. And in fact, there's a probable lurking variable existing in this whole scenario, and that would be the weather. Right? People are going to buy more ice cream typically when it's hotter, when it's summertime, when the weather is nicer. And in terms of crime rates, I mean, we're a little spoiled in Southern California where our weather really is never that terrible. But all across the country, if you're in the dead of winter, when you're not buying ice cream, you probably have a foot of snow outside that's going to make it really hard to, rob that bank that you're thinking about robbing. And you're probably not going to be committing crimes during those times when the weather is so severe. And this is just one example. There could be many other reasons why these two variables have a very high correlation to each other, or there could just be no reason at all. It could just be a coincidence. And when we're back in class next time, I'm going to show you guys some more kind of crazy and ridiculous correlations that exist in the world that can make it seem pretty ridiculous that we would ever say that one thing causes another thing to occur. But this is something we have to watch out for, legitimately. We have to be on the lookout that we're not making conclusions inappropriately based off of just saying these two variables are related to each other in some way, or they just correlate to each other. All right, but that brings us to the end of section 12.3. So when we return in section 12.4, we will be looking at doing hypothesis testing using correlation coefficients and using least square regression lines. And we'll talk more about kind of the minutia, the details of this process, go in a little more depth, and then we'll finish off chapter 12. So have a wonderful day, and I will see you all very soon.